connecting potential and field. So I'll start with that. So we can connect the potential of the charges and their field by the following. You can say that there is a relationship between electric potential. We saw earlier that the potential of a charge can be found by V equals potential energy of the test charge plus sources divided by the test Q. So we know what the potential is. We also know that the potential energy is equal to minus the work. So I'll put this here like that. So we can say that suppose we have a point charge at some point in space. What we can do is we can say that this point charge is here, so we can say that is a charge at some point in space. Suppose we have a point charge at some point in space, so this is the charge Q. Let's say this is the charge Q. Okay, so this charge produces an electric field at this point, and if we were to move some charge from infinity to a certain point in this electric field, so we shall say that this is some point which is far away, and we're moving it to a certain point R. So we're moving a charge from infinity to a point R. So this is at this point here we have dr at an angle theta, and so this displacement is ds. So we'll put this as dr. Okay, so I'll put it this way. So what we see then is that the charge moves from infinity, which is R infinity, to a certain point R in the electric field of the charge Q. So we can say that the work done in moving that charge, or in this case the potential delta V, is equal to V infinity. So let me see. We can say VR, V subscript R minus V infinity is equal to minus the integral from R to infinity of the force times dr, F dr, okay, or F times dr, which is F dot F dr. And so we shall say that dr is equal to cosine theta ds. So delta V, and this comes, the cosine theta ds comes from here. So we see that this is ds, this is dr. So if you think of it this way, this is 90 degrees, this is theta, this is dr, and this is ds. Then we can say that cosine theta is equal to dr over ds. Therefore, dr is equal to cosine theta ds. So that's what I've done over there. So I can now say that the potential V, delta V, is equal to VR minus V infinity, and then I can flip it around and go from R to infinity and make it a positive if I want. So before I do that, so F dr, so F is equal, F dr is just equal to F times cosine theta ds, which can be the integral from R to infinity of F dot ds, because cosine F times ds cosine theta is just F dot ds. Okay, and so that should take care of it. So we can say that elect delta V is therefore equal to VR minus V infinity, where V infinity is a potential at infinity which we take to be 0, and F is equal to Q times E, charge times electric field. So the Q, or this is the lowercase q, the charge that is being moved, and E is the charge that is producing the electric field. Okay, so E is equal to Q over 4 pi epsilon naught R squared. So delta V can be written as the integral from R to infinity of f, which is equal to q times uppercase q over 4 pi epsilon naught r squared. And I guess I should have just left it that way. I don't think I need to go through all that. I'm doing more than I should be doing. So at this point, so the electric field is radially out, so we can say this component, let's see, actually I can do it that way. It should be fine. So VR minus V infinity can be written as integral from R to infinity of Q over 4 pi epsilon naught R squared. And in this case, it will be, instead of R, I'm going to use S squared ds. So your book uses a notation S here, so I'm changing it to S just to make sure I'm in line with the same notation as your textbook. Oh, actually, I don't have to move any charge. Sorry. So this is E dot ds. So this should be E, not F. This is E. Put E here, not F. I'm putting E, but this should be putting F, but that is actually E, not F. I'm doing potential, not work, so my bad. I think that is, so put E, not F. So then VR minus V infinity can be written as minus Q over 4 pi epsilon naught R, 0 as from R to infinity. This is S, of course. And this can be written as, so the first one is minus Q over 4 pi epsilon naught infinity plus Q over 4 pi epsilon naught R. Okay, so this part goes away. And so we shall say the potential at R is equal to Q over 4 pi epsilon naught R. Okay. Well, the negative comes in, let me see, where did I put that? Let me see, what did I just do? When you integrate 1 over s squared ds, so it's s raised to power negative 2. Yeah.
The next one is the R is
It's s, so we are doing integral over s ds over s squared from R to infinity. So I'm using s because your book is using s. So I just switched it to S. So that is the potential at some point of a point charge. So this is 29.7 in your text. So what this is just telling us is that the potential, so this tells us that the potential difference, delta V, is equal to the electric field times a certain delta R. Because what we did was, so I can, let me see. So if the potential at infinity, V infinity is equal to 0, then this is what you should have. Then we can say that VR minus V infinity is equal to E, and this will be R minus infinity, like that. Okay, so this is R minus R at infinity or infinity, and so this is just VR equals E times R, which we can write as Q over 4 pi epsilon naught R squared times R. So the potential at that point in space is just Q over 4 pi epsilon naught R. Okay, so it gives you the same result basically. Okay, so we can continue from there. Potential of a parallel plate capacitor. So we can do this for a parallel plate capacitor. Let's do an example. So let's find the potential of a parallel plate capacitor. So this time I put a plate here. The distance between the plates is D. So that's the distance between the plates. And we are saying this is positive and that's negative. So the electric field goes this way. So the electric field between the plates of a parallel plate capacitor we know is equal to Q over epsilon naught A. or you can say the charge is sigma over epsilon naught. So sigma is just Q over A. So that's the field between the plates of a parallel plate capacitor. Okay, so we can find the potential for this parallel plate capacitor. So the potential, let's see, so the potential V is equal to the initial potential minus the integral from 0 to D. So we can say this is, so in your book they use this as 0 and this is S. So we can say 0 to S of E ds that way. Okay. So we are going from an initial potential which is at 0, and this is the potential is V. Okay, so potential at the initial potential should be equal to 0, and then the final is V. So the plate has a potential difference of V on it. So this is equal to V initial integral from 0 to S, and S is just a distance between the plates, but we'll get to that shortly. So this is going to be Q over epsilon naught A ds. So this is V initial minus Q over epsilon naught A times S, okay, 0 to S. So we can say V initial minus QS over epsilon naught A. Okay, so this is your potential for at some point. So we can say that V equals V initial minus Q over epsilon naught. Q over epsilon naught A we know is an electric field. So we can say that equal to E, and then we have S, where S is the distance between the plates. So we can say V final, so V is equal to V initial minus ES. And if we take V final minus V initial, then we can say that V final, so it goes from positive to negative, so actually the negative terminal is 0, so electric field is going from right to left, so it's going from positive to negative. So we can say V initial, so we say that V final is equal to 0, therefore V is equal to ES. The field is going from positive, so the potential between the plates is just equal to E times S. So S is the distance between the plates. That distance is D. So if you want to use that, then you can say that the potential V is equal to E times D. Questions at this point? Okay, so let's go to sources of electric potential. Next chapter. So this is 29. Actually, it's the same chapter, 29.2. Sources of the potential. Okay, so electric potential is just basically the potential of the battery. So, or if you have a charged capacitor, then you can put a certain amount of potential on it. So it acts like a storage for charge. The capacitor just stores charge. So if you discharge the capacitor, all you are doing is forcing that charge to flow. So it allows a current to flow through a circuit. And so the capacitor acts like basically a battery. So if you have a camera, if you remember those flash cameras, what you have is you have a battery in there. So if you wanted to use a flash, basically what the camera is doing is that it uses a battery to charge up the capacitor, which is the flash. So when you take the picture, you are discharging the capacitor, which then releases its charge and it causes the charge to go through a bulb which flashes. So that's what is happening there. So basically the potential sources are batteries, that's one source, or you can have capacitors, and different types of capacitors are shown. We have the usual one that we've seen, but the Graaff generator is also another way of producing charge on some sort of device, which is like a capacitor. So Graaff generator is another source of potential. So we'll see that batteries and generators or capacitors are sources of potential. So there are various potential sources. You can say that the capacitor can be charged so that it stores the charge for later use. Another source of potential is a Van de Graaff generator. You can say that a Van de Graaff generator produces a high voltage or high potential when charged, and then we can say that a battery is the most common source of potential. So let's first consider the capacitor. So if you remember, we always had a capacitor this way, and then we shall charge it. So we will charge the capacitor with the battery like that. So this is the positive terminal. So that puts a positive charge on this plate and a negative charge on that plate. So that means we have electric field going this way. So what we can do after charging the capacitor is just to disconnect the battery. So this is charging. So after the battery is disconnected, you're going to have just a capacitor which looks like this. So it will have a charge on the plates. Okay, so it's charged. So if this capacitor is connected within a circuit, so we can say this is charged. Now if we connect this capacitor in a circuit, what will happen is that the capacitor can be discharged. So we can say that we have this capacitor here, positive and negative, and we connect it with a switch through a bulb to this terminal here. So this is a switch. Okay, so this capacitor is charged and there's a switch. So if we close the switch, if you close the switch, then the bulb comes on, at least briefly, because the capacitor discharges through the bulb. Okay, so current is going to flow through the bulb and the capacitor discharges. So the negative charges move towards the positive and the capacitor discharges through the bulb and produces, and so the bulb will flash. Okay, so this will be like a flash. So when the switch is closed, then you see a flash. So that's one use of a capacitor, of course. Then you can just have, next we look at the battery. So we shall have the battery this way. Actually, let me draw a real battery. So let's say we have a battery like that. So this battery is connected in a circuit. Let's say this is a light bulb. So we have a switch, and that's there. So this is positive and that's negative. Okay. So if the switch is open, there is no light. And if we close the switch, we go like this. So this time the switch is closed. When you have a closed switch, then you can have the light, of course. The light comes on. Alright. So that's the way. And then of course, depending upon how many batteries you have, if you have 2 batteries in there, the light is going to be brighter. If you have 3, it's going to be even brighter, and so on. Okay. So the potential of the battery is just equal to the work done by chemicals in the battery to move charge. So the potential delta V of the battery is the work done by the chemical energy, W chemical, to move the charges. So we can say that W chemical is equal to potential difference times Q. Okay, so that is so the potential delta V is equal to W chemical divided by Q. Okay, so that is the work done by chemical energy to move charges Q. That's for an ideal battery. For a real battery, there's going to be some resistance. We shall see that later. So this is, we can say that a real battery will have internal resistance. Okay, so what we have here is that delta V is equal to the chemical energy per unit charge, and this is equal to the EMF. Okay, so delta V is equal to EMF for ideal battery. On the other hand, delta V is less than the EMF for real battery. Alright, I think that should do it. Let me see, where are we now? 750. Let's see. Okay, so let's go to the next section. A few more items there. Okay, let me just finish this. So, so suppose we have 2 batteries connected together. So we shall have the following. So we have a battery this way, and then we connect the second battery this way, a light bulb again, and a switch. So this time we have the two batteries. This is delta V of 1. This is delta V of 2. So the total potential is going to be the sum of the potential for the two batteries, like that. So those two batteries are connected in series. So if each of these is 1.5 volts, then we can say the potential difference is equal to 3 volts. So with 3 volts, the bulb is going to be brighter or twice as bright as when you have just one battery in there. So it's going to have a lot more brightness.